So let's consider now a cantilever with a length of 6 meters and loaded by uniformly distributed load of 5 kilonewtons per meter. So the objective is to calculate the bending moment diagrams, the shear force diagrams, and the axial force diagrams. So let's start by computing the reactions. So I should have a vertical reaction here, AY, AX, and a moment. I'm going to use the traditional referential for reactions, and I can say sum of vertical forces is equal to 0, means AY minus 5 times 6 equal to 0, coming AY equal to 30 kilonewtons. Sum of horizontal forces equal to 0 comes minus AX equal to 0. Sum of moments around point A, I get a moment. This one does not cause moment because it goes through point A. This one does not cause moments because it goes through point A. And the uniformly distributed causes a negative moment of 6 times 5, which is the resultant, times the distance 3 equal to 0, comes the moment reaction equal to 90 kilonewtons per meter. So let's clean this up. And this one is 30, this one is 90, this one is 0. And I don't need any of this again, so let's delete all this. So now let's calculate the diagrams. So I'll have the normal force, shear, and moment. If I look at this section, and now since I'm working with internal forces, the positive signs are this for shear, this for normal, this for moment. If I look at axial force, so forces parallel to the bar, to the left of this section and pink, I have no forces parallel to the bar. So the axial force here is 0. If I look to the left at the green sections, the sum of all forces to the left parallel to the bar is still 0, which means the axial load is 0 and 0 and 0. This is actually true for any section I choose. So the axial force is actually equal to 0, so there's no actual axial force. When it comes to shear, if I look to the left of the section A, I have a force of 30, which according to this referential here is negative. I put negatives on top, positives at the bottom. So the initial one is 30. So now, if I look here at the section in green, I have the 30 minus this distributed force. So it's going to be smaller than 30 because they go opposite ways. I know that dV dx is equal to P, which also gives me that the change in shear is the area below the distributed force. So this one tells me that if p is a constant function equal to 5, v is linear. This one tells me that the change in v is the area of this distributed force. So this distributed force is worth 5 times 6, 30. So it comes from 30 and it linearly moves down from 30 to 0. The bending moment, if I look at all the bending moments to the left of section A, I have this one, 90, which in this referential, or this convention actually, is negative, so 90. Again, I can use similar equations, dm dx equal to minus v, which means that the change in moment is equal to minus the area below v. So the area below v is 30 times 6 divided by 2. 30 times 6 divided by 2, that's equal to 90. So this is gonna, if this is negative, this one increases, so it goes down, increase 90, so it comes from 90 up to 0. If v is a straight line, so it's a first degree polynomial, it means because of this that the moment is a second degree, it's parabolic. And the derivative, or the slope, at the beginning shear is 30, means the slope of this is 30, very high. At the end, shear is 0, meaning the slope at the end is 0, meaning horizontal. And we get something like this.